This is the video for 4.2.2, the physical interpretations of the mean value theorem. There's no new definition, no rules or theorems here. We just want to interpret the MVP in a slightly different approach. So we want to start like this. If we think about the difference quotient, f of b minus f of a over b minus a, as the average change in f over a, b, the closed interval, and f prime of c as an instantaneous change, then that mean value theorem says that the instantaneous change at some interior point must equal the average change over the entire interval. So what you see here is, rather than the interpretation as an average rate, as an instantaneous rate, we leave those words out. We think about an instantaneous change of a function, an average change of a function. What we're going to see is that we can apply the mean value theorem to real scenario functions that have real values on x and y intercepts, and notice that the MVT tells us some real interesting things. Let's quickly review what the MVT tells us. It says that if we have a function that is defined on some interval from a to b, that there exists some point in the middle of that interval where the average rate of change is equal to the instantaneous rate of change. In other words, if I were to look at the slope of this secant line that is between the point a comma f of a and the point b comma f of b, and I grab that slope, we know the slope is f of b minus f of a over b minus a. MVP says there exists some point between a and b, say right here close to the middle, call it C, where if we look at the tangent line and grab its slope. So we know that the slope of a tangent line is the derivative at that point. So it's just f prime of c. Mean value theorem says that there is a place where both of these lines have the same slope, where the average change of the function is equal to the instantaneous change of the function, that f prime of c is equal to f of b minus f of a over b minus a. So the first paragraph here on the next slide is the same, but this is moving us into example 4. There's nothing really for us to do here other than interpret a function and its graph. If a car accelerating from 0 takes 8 seconds to go 352 feet, its average velocity for the 8-second interval is 352 divided by 8, or 44 feet per second. And that's this function on the left in blue. So this is a position function of a car. It is an x-axis function of t, time in seconds. It's a y-axis function of s, which is distance in feet. So then over that first 8-second interval, its average velocity, or AROC, would be its total distance, which is 352, over the total time it takes, which is 8 seconds, for 44 feet per second. So the mean value theorem says at some point over that 8-second period, the speedometer must read exactly 30 miles per hour. Why 30 miles per hour? Well, because that's what 44 feet per second is. So we're going to say this is actually 30 miles per hour. And hopefully that makes good sense, that if you are speeding up at some point before you reach your maximum speed in miles per hour, you're going to hit every one of the miles per hour in the middle. So at some time between 0 and 8 seconds, there must have been a place where the speedometer read exactly 30 miles per hour. And that takes us to an exercise from the text, number 11, on speeding. A trucker handed in a ticket at a toll booth showing that in 2 hours she had covered 159 miles on a toll road with a speed limit of 65 miles per hour, and the trucker was cited for speeding. Why? So let's take a look at this trucker's average rate of change, which would be given by the total amount of miles that she traveled, so 159 miles, over the total time that she spent driving it. So a toll booth showing in 2 hours. So the total time is 2 hours. And this is going to be equal to a rate in miles per hour. Let's quickly do that since it's a pretty easy division problem. So that's going to be a 14 here and a 19 there, and then 2 times 9 is going to give us what, an 18 here with a 1 there. So we've got 79.5 miles per hour. So her average rate of change over that period was 79.5 miles per hour with a speed limit of 65 miles per hour. Trucker was cited for speeding. Why? Well, the MVT, the mean value theorem, says that because the average rate of change over the 2 hours was 79.5 miles per hour, at some moment in that 2 hours, the speedometer must have read what? 79.5 mph. So here we have calculus proving to us that even though we didn't have a radar gun, we still could give a ticket for this car driving along, because if we know its average change over that interval of 2 hours, then we know that at some point the instantaneous change had to have been the same. So if we went 79.5 miles per hour on average, at some point we were going 79.5 miles per hour at a moment. So that ends everything here for this second video in 4.2.